Yeah, good morning, everyone. So I will talk about several results which are loosely connected by the topic, but in fact these are three different papers, and I will try to highlight the main ideas. So approximation of high-dimensional probability distribution, this is a very important task at the moment in many application areas. So probably the most popular now is machine learning and approximation of distributions of images, for example. So you have now access to very large databases of what is a real image. So the modern networks, they use the modern models. They work mostly with, not say mostly, but they can work with data set of size as the whole image, amount of images on the internet. So then you have to clean them, maybe some of different qualities and so on. So there are different data sets, but more or less you have a lot of samples. And these samples are very high dimensional, right? So each sample could be an image, which is 512 times 512 times 3. Or you may go to images of high dimension. So these are vectors in very high dimensional Hilbert space. And the goal of the generative modeling is to learn the distribution from which these samples are taken. So we want to parameterize somehow by a certain low dimensional vector Z an image. And learning this generative network, generator is an important task. So if you do this, then you can use these techniques in really many areas, not only in images, but also in videos, in audio, even in text processing. And many what is called AI now is using in one way or another these techniques. So, and if you learn the probability distribution with the likelihood, I will talk about it later, then you can also add this as a regularization term, for example, to improve images, to improve the quality of the images, do super resolution, do deblurring, and many other tasks. So what probably most of you have seen is the generation of images. So all these people, they do not exist. So these are just synthetic images given as an output of a certain neural network. And the quality, again, goes up. The quality goes up with every month. So every month we see some new paper which improves the quality of the generation of images. However, training such models is not easy. And also understanding how the methods that train such model converge is not a trivial task. So we will focus in this part of the talk on the theoretical study of the convergence of training such models. But before, of course, going into the details about the theoretical analysis, let me just introduce the basic model. This was the first model proposed by Young Fellow in 2014. And probably this was one of the first results that was not known before in this deep learning revolution. And the idea is how actually we learn the mapping from a certain known distribution, typically a certain low dimensional normal distribution with zero mean and identity covariance matrix is taken. This is low dimensional, maybe 128. Then a mapping generator, and creating an architecture for the generator is a difficult task, but we now suppose this is a certain function which maps RD to Rn. So it inputs a random variable from a standard distribution and outputs what should look like a sample from the distribution for which we have already samples. We do not know the density function, we do not know anything, we just have a lot of samples. In this case, is the images of the digits. This is a standard toy data set called NIST. So, but we need to introduce, and this generator has some parameters theta here. So we need to find optimal parameters. So how we do that? We need to have a certain loss functional for these parameters, and since we do not know the density, we cannot use likelihood. But what we can do the following, and that was the idea, and I think this is really a brilliant idea, that we now have real samples and now have infinite amount of fake samples, which should look like the real ones. So this is a binary classification task. So we introduce a second function. Typically, it's a neural network, but in fact, it can be any parameterized function, which is called discriminator. And the idea of the discriminator is to solve binary classification task to distinguish between real samples and fake samples. So for real, it should output class 0 and fake samples class 1. So they're playing now this adversarial game. So the generator tries to fool the discriminator tries to distinguish. And if you do it in the right way, the generator will learn to generate ideal images that not a single discriminator will be able to distinguish. So the discriminator should always lose in this game, and the generator will be able to generate perfect images. So that's the setup. Then you, of course, have to introduce the loss function here. And, well, the first loss function was just the binary entropy loss. So the generator outputs, or the discriminator outputs the score 0, 1, which is the probability of the image being real, right? And that's the loss function. And many more loss functions have been proposed, but the most important thing is that you have the discriminator tries to maximize the classification accuracy while the generator wants to minimize. This is a min-max problem. This is a saddle point problem. And solving such kind of task is not an easy task. So typically how it is solved in machine learning, and I think, so there are still many papers that try to improve over this basic approach. And they claim that they're able to do that, but still there is nothing much better, and practitioners, they use only this. So they use gradient descent accent. What it means, you freeze the discriminator and you make the gradient descent step in the parameters of the generator, and then you freeze the generator and make the gradient accent step with respect to discriminator. Then you can play with learning rates and how much steps you do. Maybe you introduce some inner optimization, but overall, independent of, well, maybe 10, I know maybe 10 or even more papers that try to build a more advanced method with momentum and so on, but still in practice, nothing works better than gradient descent accent. So there is, I think, still room for development of more advanced optimization method for this task. If it would be convex concave problem, that of course there will be a lot of nice algorithms, but it is not convex concave. So that's an open thing. So the general form of the functionals that are used in this domain is the following. You have to solve a min-max problem, which depends on two functions, the discriminator and generator. And this function is the sum of two terms. The first term is the expectation with respect to the real samples. And there is a certain pointwise function of the d of x. And there is now the expectation over the fake samples. So I have shown you this logarithms, but also it can be just maybe the norm of a minus 1 squared, something like that. Actually, many options. And different models, they use different losses. So for example, there is a so-called style gun paper. They use, I think, something like quadratic here and some logarithm here. So there is a big, so these functions, property, it's quite easy to see what should be the properties of function in order that the Nash equilibrium of this problem corresponds to the real samples. But I think I'm just not going deeply into the details of that. So our idea, so typically at this step, the discriminator is parameterized by a certain parametric form, typically neural network. The generator is parameterized by a certain neural network. And then you do this gradient descent ascent. So our idea was very simple. Let's not assume any special form for the discriminator and generator, but assume that there are certain functions. So it's a good question from which functional classes this function should, to which functional classes this function should belong. And in the paper, we have some formal stuff for that, but in the talk, I just want to omit it. So assume that everything that we are writing here is legitimate. So what we do, we write down the continuous gradient descent ascent in the we write this gradient ascent descent in the continuous time. So the derivative of this function is the variation of this functional with respect to d, which is actually, well, simple to compute, but you get not a very nice looking result. If you do it just directly, you do not get anything useful. And then the derivative of the generator is the variation of this functional with respect to the generator itself. So we're interested in a very specific task here. We're interested in the local convergence. So we assume that this dynamics, when time goes to infinity, that the discriminator converges to 0, so the stationary point, and the generator converges to a point where d of j of z is distributed like our target distribution mu. So there are simple condition of phi1 and phi2 that at least this is a stationary point. So, and the question, what is the local convergence here? Since this is a saddle point problem, it is quite easy to see that such dynamics can be oscillatory. So what we need to do, we need to linearize this dynamics around the equilibrium point, get the operator, and analyze its eigenvalues. And depending on the eigenvalues of this operator, actually see what's the dynamics, what's the oscillation. And when you train in practice these generative adversarial networks, you often see this sort of oscillatory convergence. You may have some measure of accuracy, and then it just does like that. And this is clearly due to the presence of these imaginary eigenvalues. And well, such kind of analysis has been done before, but assuming there is a certain parametric form for the discriminator and generator, and then you get some ugly looking saddle point matrix with no specific structure. But if you write down just for this particular functional, then the resulting linearization of this dynamics has a very simple and intuitive form, and that's what I would like to talk about. So in order to get the linearization of this dynamics, it is sufficient to build a local quadratic approximation of this functional around the equilibrium point. So with a little bit of machinery, you get the following linearization. So the linearization, you get a functional which depends on these parameters, which are the small perturbations. I will explain what they mean. With high order terms, you can, so you need to have certain higher order derivatives in order for this to hold, at least for the straightforward derivation. But this functional has a very simple, so here rho is the same as mu. So there's this misprint. So this is the functional, it's quadratic, well as expected. So you have some parameter alpha, and this parameter alpha is a certain derivative of this function phi1 and phi2 at the point 0. So this is just some number. And here you have the expected value with respect to our measure of the square of u. So it's just the integral rho u squared. So this is a clear thing. And here you have this term which corresponds to the rotation stuff. So this is the weighted scalar product, again, with our target density rho of the gradient of u times v. So that's the scalar product, weighted scalar product. So what's so u is clear. U is just the stationary value of the discriminator, which can be selected to be equal to 0, plus the displacement. V is a little bit more tricky because we had the mapping from the normal distribution to the target distribution. But if we are sufficiently close, so here are samples from the real distributions, here are samples from the fake distribution, and V is the displacement field. So how we sample X from our density, from our measure, that actually it's not so important. We can actually do all the same machinery if our target distribution doesn't have a density, but only has some measure, but it's not important. Then how you need to perturb the sample to get the samples from the perturbed density. So that's how this linearization can be written in a nice and compact form. So this is now quite simple quadratic functional, and we need to find a saddle point of this function, which is actually, of course, u equal to 0, v equal to 0. So we need to analyze the dynamics of the gradient ascent descent for this function. So if you just write this all down, and here it's given in terms of in the assumption we have the density, that's what we get. We get the following system of equations. And so this is a picture for a very simple min-max problem, two-dimensional, which shows that such kind of system can show the oscillatory dynamics. Here you have a system of linear partial differential equations, but this equation is actually a wave equation, right? If you divide this equation by rho, you get u dot equals minus alpha u plus 1 over rho beta, the divergence of rho v, and then you take the second derivative, u double dot equals minus alpha u dot plus 1 over rho beta gradient of rho beta squared gradient of u. So this is the second order derivative, this is the damping term, and this operator is actually a weighted Laplace operator. So if you write down the quadratic form corresponding to this operator, it will be very simple. And this, with respect to the scalar product with the same weight. So the norm is this one. So you get a very simple expression for this dynamics, and you can analyze the eigenvalues of this operator just by analyzing the eigenvalues of this weighted Laplace operator. So in the strong form, this Laplace operator is this. And with it's self-adjoint with respect to the scalar product, weighted scalar product. So it has a complete set of non-positive definite, of course. So and it has Neumann boundary conditions. So it has one eigenvalue that is constant, and then you have other eigenvalues that actually determine the dynamics and the eigenmodes which determine the convergence. So here are some illustrations for different manifolds, uniform density. And actually the convergence is completely determined by this vibrational mode. So if you consider the data set, these are points lying on a manifold, and maybe weighted manifold. So the convergence of the straining of GAN is completely determined by the vibrational modes. And then you get the explicit formula for the eigenvalues because it's just a linear operator. So you need to solve this quadratic equation. An interesting thing, there is one well-known regularization technique that says, okay, the discriminator, so the penalty on the norm of this discriminator is added. If you add this, you actually get the same eigenfunctions, but you modify a little bit the eigenvalues here. And then the most interesting conclusion here is that you can actually select the parameters alpha, beta, and gamma in such a way that the damping will be quite high, and this operator will not have imaginary eigenvalues. So all the eigenvalues will be real, and there will be no oscillations. So typically, well, people construct the loss and say one loss is better than another, but our conclusion is different, is that the parameters of the loss, which determine alpha and beta, so the loss functions phi1 and phi2, they determine alpha and beta. Their influence on the eigenvalues also depends on the eigenvalues of this vibrational Laplace operator. And mostly they depend on the smallest non-zero eigenvalue of this Laplace operator, which is also known as Poincare constant. So it's the term in such time of inequality subject to integral of rho u equal to 0, sorry. So this minimal eigenvalue, and this minimal eigenvalue geometrical meaning is also quite clear. It's how the manifold is connected. So if the manifold is well connected, this eigenvalue is large. If it's small, then it can be brought into two disconnected clusters. So if you just make this term equal to 0 for the minimal eigenvalue, then you will not have imaginary eigenvalues, you will not have oscillations. And well, okay, the selection of optimal parameters, this is only, they are only optimal locally. So we cannot claim that these parameters will be good for global convergence, but locally this is here. And simple, well, numerical illustrations show this. So if you just take the mixture of two Gaussians, and if they are separated, this smallest Poincare constant is small, and if they are well connected is larger. And this is how the optimization converges, right? So there is something happening in the beginning, but then if you have larger Poincare constant, the convergence is faster. Then something is happening here, but this is due to stochasticity of the implementation and so on. But the convergence, well, is clearly faster if you select these optimal parameters. So this is a model example. Some practical thing that comes for the sort of big machine learning is that our conclusion is that the larger Poincare constant, better convergence. And I don't know if you're aware or not, but in one of the popular topics in deep learning is that when you train these models, you add artificial data to the data set. So you take images, you rotate them, you change the color, you scale them. So these are just adding some artificial samples to the data sets. So in the terms of the density, you change the density, you change the manifold. So the hypothesis to check is that if we add the augmentations in such a way that the Poincare constant increases, and evaluation of Poincare constant can be done in a very cheap way, then you should get better quality in terms of some metrics. So this is so-called Fréchet inception distance. And you see it, for example, if you increase the red channel, so the Poincare constant goes down and the fit score goes up. So there is this correlation between some metrics, metrics of these GANs and this fundamental geometric property of the manifold. So this is sort of a practical thing, but overall, I think something else can be done. So this was published in last year. So I still have some time, so I need to cover two more parts. So this is our paper, which actually connects learning and tensors. So Sergei Dolgov and his co-authors did a lot. So what we did, we tried to make a generative model which solves exactly the same task. You're only given samples and you try to approximate the probability distribution. So this method has limitations, which I will talk about later, but we assume that we can fit this distribution as a linear combination of a certain basis functions. And we select a tensor product basis function. So we do not assume that these coefficients are sparse and so on. However, so the coefficients, if you have a tensor product basis functions, they can be naturally arranged into a big tensor. And we put low rank Tensor-train constraint on this. So we have this object now, and we need to learn the parameters, which are now the cores of the decomposition in order to fit the distribution. And this special form of the distribution allows us to use different basis function, different loss function. So we do not need to have this adversarial training, because so the loss that we have is just, the integral between the unknown true distribution and the target distribution squared. So that's the loss that we are using. And if you just expand it, you get the integral over this target distribution, you get the expectation with respect to the samples, and you get the constant that doesn't depend on the parameters. So this can be evaluated fast in the format, this can be evaluated from samples, and all these terms are cheaply computable. So this loss is computable. So in order to train this, you need only to solve a minimization problem, not an adversarial training problem. So one problem, and we worked on this quite a lot, and only recently we managed to make it work for some practical examples, is that the Tensor-train, the density should be positive. And the Tensor-train model is not positive. If you just take the square of the Tensor-train and use it as a parameterization, in fact, all the terms can be computable, but the complexity with respect to the rank does not grow significantly. This is actually an interesting thing, quite technical, so I will skip it. So the details are in the paper, but this solves the problem of non-negativity. There is a certain comparison with other methods. So our method is good in many things. So you can do sampling from such kind of distributions. So you have the likelihood. You do not need to have this adversarial training, and you also can compute marginals quite easily. So there is, of course, a minus in that. It doesn't scale up to thousands of the dimensions, but if the dimension is tens, maybe 100, it works very well and beats all the other methods significantly. So we did it. And so these are toy distributions. So actually, this model can learn quite well complicated things from samples. And also, well, these are maybe, let's go to higher dimensional things. So there are the standard distributions with dimensionality ranging from 6 to 64. And we were able to get, well, at least not for all, but for some, we were able to get better likelihood. So here, we actually did not get the best likelihood, but in other metrics, our distribution was better, but that's a separate story. So for this 6-dimensional data set, this is the dependence of a certain metric between two distributions, and the computational time with and ours is much faster to reach. So the computation in this tensor format is much faster, as well as the sampling. So sampling is much faster. So this is a useful tool for the data that is given as a, well, in a tabular format. So if you go to really thousands of the dimensions, they start not to work so good, unfortunately. But for dimensions up to hundreds, this method works quite well. Okay. So this is the reference was also published last year. And yeah. I was maybe too fast on this part, but anyway, maybe being faster is not worst in this case. And the final thing that we were doing with respect to modeling high dimensional probability distribution is this one. And it's related to the solution to modeling the densities of distribution obtained from stochastic differential equations. So in the most general form, you have a system of SDEs with a certain deterministic term and stochastic term, but I'll just say we'll focus on the case where this is just a standard Brownian motion. And these models are actually quite popular nowadays in, well, so to say, mainstream machine learning. These are called diffusion models. And they, in terms of representing the image quality and so on, they beat the generative adversarial networks, and they also have many other nice properties. So what do I mean by that? So basically, this is a side note, why these models are important in machine learning nowadays. So you take an input distribution here, which is, for example, images, then you run the diffusion, maybe a very simple one. So which converges to the normal distribution. And then you approximate the density at each time step, the density of this cloud. And then you run the deterministic reverse diffusion, which has exactly the same marginals. And this is extremely computationally heavy, so you need to spend thousands of GPU hours, but in the end you get models of extremely high quality for representing images, and they also have likelihood. So this is but of course these models, they have many other applications besides this one. So the goal is to have certain starting density, and you want to approximate the density at time t. And it's well known that this density is subject to this Fokker-Planck equation, which is a high dimensional equation on the density. And well, with Sergei Dolgov and Boris Khrulkov, we tried to solve it using just, I would say, direct tensor methods, where you represent the operator in this form, then you construct the time stepping scheme, and it worked quite well. But we actually proposed something that is, well, computationally more efficient. And we actually used it for this application of modeling the intermediate diffusions in another paper recently, which I'm not talking about today. But basically the idea, so again, we parameterize the density with the Tensor-train decomposition. So you introduce the tensor product grid or basis, you have the tensor. So we use Chebyshev polynomials, tensor product of Chebyshev polynomials. Then we introduce low-rank constraint on the factors, and we need to evolve this in one time step. And the equation is basically, I think it's written on the next slide, but well, it's the Laplacian term plus the convection term, right? So this comes from the Brownian motion, this comes from the diffusion. So what we do is just do splitting. So we make a step in this, well, we use the strength Marchuk splitting, so we make half step in one and so on. So this making a time step for the heat equation in the tensor format is super easy, and it has been done by many authors. So basically rho of t plus tau is just the exponent of delta t rho of t, right? And delta is just, well, let me do it in one dimension. It's the sum of, in two dimensions. In sum of Kronecker products, right? And the exponent, the matrix exponent, is just the Kronecker product of one-dimensional exponents. So, and if you apply it to the tensor product representation, the ranks do not change. Oops, sorry. A small failure here. Anyway. Sorry. So applying this step in diffusion doesn't change the rank. So the most interesting part is then to make a time step with this term. But it corresponds to the deterministic diffusion. We go probably one step further. So it corresponds, this step corresponds to the deterministic diffusion of the density. And we can write down the equation for the diffusion in the Lagrangian coordinates for the diffusion of the, not for the diffusion, for the evolution of the density along this trajectory. So you have a point, it moves somewhere, and the density, and if you know the density here, you know the density here. But we need to evaluate the function on a grid, right? So we need to have the value on this in this point for the next time step. So we just solve this linear system backwards in time. So somewhere here. So we get the coordinates, so like semi-Lagrangian method. We evaluate all the density here using the Chebyshev interpolant, and we can evaluate the function, the density at the next time step at any point with the cost of solving one small ordinary differential equation. And this is ideal for the so-called Tensor-train cross approximation method, which allows you to build the approximant from a few number of samples. So that's exactly what we do with some technical tricks, because you can do it somehow speed up. You have a nice initial approximation, but basically your sample dnr squared elements from this grid and recover the density at the next step. So that's why it's called the cross approximation, and this is very cheap. So if you do it sort of in a normal way, the complexity with respect to rank will be much higher. So that's basically it. And well, the method works. So this is some example, I think, in 3 dimensions for the computation of the so-called dumbbell example. And the rank during the evolution was very small. And it also was published at the end of the last year. So this is a useful tool because it allows, if you just have an SDE, you can come up with approximation of the density quite fast and accurate. And for dimensions, maybe again, 2, 3, 5, 10, something like that. It can be used in a robust way. Of course, if the density can be well approximated in the low rank format, if it will not, the ranks will just grow to a very high number, but that's the typical thing for this case. And if they don't grow, then the method is applicable. So that's all for my talk. So thank you for your attention. I'm happy to answer your questions.